Swayam Prabha. Digital India. Educated India.
So, good morning and welcome to the fifth lecture on the subject of digital signal processing and its applications. We will just spend a minute or two in recalling what we did the last time. We will take a couple of questions and then we will proceed to discuss what we intended to in the lecture today. In the previous lecture, we were looking at the whole idea of discrete systems. And before we started talking about the properties of systems, we thought it more appropriate to find out what we wanted out of the systems, at least at the first glance, in the first step of design. What is it that I would expect from a system if I wanted to be able to succeed in the process of design? And in fact, we put down certain requirements. Let us summarize those requirements. So, this is a summary of the previous lecture. The theme was, what do we want from a system? And the answer was contained, or in fact the answer was completely captured by the following three experiments. We said, experiment 1, we have a discrete system. We give it a complex exponential or a phasor, which we can denote. We will use, just for variety of notation, we will use the following notation today. We agreed that we insist that the output should also be a phasor of the same frequency. Let us call it B1 e raised to the power j omega 1 t plus, let us call it psi 1 here. And in fact, now we will use a shorthand notation. We will say we will perform experiments 1 and 2, in which we respectively have A 1 and 2, omega 1 and 2, phi 1 and 2. You see, so this is a shorthand notation for capturing two experiments of a very similar nature in one drawing. Okay? You must interpret when you read something like this. I have intentionally brought in this notation here because it is useful to use this notation where you have very similar drawings to be repeated, or very similar expressions or equations to be repeated. What I have drawn here is two systems or two experiments with the same system in one drawing, and the way you read it is, read it with the comma denoting respectively. So, you say experiment 1 respectively 2 has A 1 e raised to the power j omega 1 t plus phi 1 applied respectively. In the second experiment, it would be A 2 e raised to the power j omega 2 t plus phi 2. It is the same discrete system in both the experiments, and the outputs are respectively B1 e raised to the power j omega 1 t plus psi 1 and B2 e raised to the power j omega 2 t plus psi 2. Right? So, one must read it like that. So, two experiments written down. And then the third experiment, or the test experiment, which determined whether we wanted, whether we got what we wanted from the system, is same discrete system, I gave it the input C1 e raised to the power j omega 1 t plus alpha 1, let me call it that, plus C 2 e raised to the power j omega 2 t plus alpha 2, and I ensure that what I get was d 1 e raised to the power j omega 1 t plus beta 1, if you please, plus d 2 e raised to the power j omega 2 t plus beta 2 with the following relationships, which we are now going to write. D 1 by C 1 is the same as B 1 by A 1, and of course, we write two equations all at once here, and beta 1 minus alpha 1 is equal to psi 1 minus phi 1, and similarly for 2. Do we all agree with this? This is what we wanted. What are we saying in words, or in a verbal description? What are we trying to say here? We are saying that firstly, when I have a combination of rotating complex numbers applied to the system, I get a combination of the same rotating complex numbers appropriately changed in amplitude and phase. And the change in amplitude and phase is independent of the original amplitude and phase. The change in amplitude and phase is described by the system, not by the particular amplitude or phase that you have given it. You see, at an even higher level of thinking, or at an even more abstract level, what are we trying to say? We are saying that we can deal with each rotating complex number rotating with possibly different angular frequencies in its own right. So we don't need to, we don't need to worry about what is happening to the complex number rotating with some other angular velocity when I am dealing with a complex number rotating with a particular angular velocity. I can deal with them in a decoupled way. Now, going down even further, why did I come first to the question of complex rotating numbers at all? Because I want to deal with sinusoids. And why did I want to deal with sinusoids? Because there is a large class of waveforms which I can think of as a combination of sinusoids. And why is it that I am so fond of sinusoids, or why is it I am so fond of thinking of waveforms as a combination of sinusoids? Because sinusoids are extremely smooth, sinusoids are convenient to deal with, and if you can think of waveforms as a combination of sinusoids, I can deal with the waveforms more appropriately from what I want to do with them. So, I gave you the example of separating out male and female voice components in an audio piece, which can easily be described in terms of its sine wave composition, right. So, many physical circumstances, many physical descriptions of systems require thinking of the underlying waveforms that we are dealing with in terms of the sine waves that comprise them. And therefore, it is convenient if I can build a system design philosophy which rotates around what the system does to sine waves. And what I want is further that I should be able to specify in a decoupled way what the system does to each sine wave separately, without the other sine waves interfering in the process. So, this is the whole story. This is where we are at the moment. As I said, you see, the next thing that we are going to say is often present in textbooks, but it is often not clear why we look for those properties. The next thing that we are now going to say is, if we want to get this from a system, to get this, we need linearity and shift invariance. In fact, we need three things. We need linearity, we need shift invariance, and we need stability. And today our objective is to deal with these properties. What do these properties mean? So, these are the questions that we had posed in the last class, and we are now going to answer them. Is that right? So, let's first take up property number 1, linearity. What does linearity mean? Linear, in fact, linearity is an oft quoted property in the context of systems. And in one word, linearity is summarized by what is called the principle of superposition. Literally, the word superposition means putting one on top of the other. Superpose, when I superpose one upon another, I am putting one on top of the other. And the mathematical meaning of superposition is the following. Here again, I conceive of three experiments, and I am more abstract now. I have this discrete system. I shall denote that discrete system by script S, as I have done here. I apply to it in two different experiments. I shall now number them experiment 1 and 2. The inputs x1 and 2 of n, and observe the corresponding outputs y1 or 2 of n. Again, I am using what I call multiple concept notation here. I am using this notation to condense my drawings. The test experiment is to take the same system, give it alpha x1 n plus beta x2 n, and ask what the output is. If the output is also alpha y1 n plus beta y2 n, and this holds, now I bring in one more notation. I bring in this notation to denote for all. For all x1, x2, alpha, beta. Alpha and beta are in general complex constants, x1n and x2n are in general complex sequences. We know now why we have to allow for complex sequences. We have agreed to use rotating complex numbers in place of sine waves. So, I must allow for complex sequences. And if I am allowing complex sequences, I must also allow complex constants. Needless to say, real sequences or real constants are a special case. Is that right? Now, what we are saying in the principle of superposition is, when I superpose by virtue of linear combination two inputs, so I take any linear combination of two inputs and give it as the input to the same system, I get the same linear combination of the two outputs. Not only this, this is true no matter which two inputs I took and which alphas and betas I used. Now, important thing in superposition is the for all part. I must stress this right in the beginning. It might very well be true that the system exhibits this property for some specific x1 and x2, but that does not satisfy us. It is only when the system unconditionally exhibits this no matter what x1, x2 are and no matter what alpha and beta are, that we are convinced the system is linear. If there is a violation even for one particular case of x1, x2, alpha or beta, we must classify the system as non-linear. Now, we can reflect a minute on why this should be required. One thing is very clear. The condition that we had put on the system a couple of minutes ago is very similar to what we are saying right now. In fact, what we are saying right now is a kind of more general statement on that condition, isn't it? There we were saying this for the context of rotating complex numbers of phasors. Now, we are saying it for any inputs x1 and x2. You see, it is clear that if the system is linear in the way that we now understand, quite a bit of what we asked for a few minutes ago in connection with rotating complex numbers seems to be satisfied intuitively. quite a bit of it seems to be satisfied. However, this is only intuitive, this is not really rigorous. We are first going to build ideas by imagination or intuition, and then we are going to put down rigorous proofs, right. Intuitively it is clear, we are asking for some kind of a linear combination there of two rotating complex numbers rotating with different angular velocities, and we got the corresponding outputs there as we expected here. I want to emphasize another point here. You see, when you talk about x1n, x2n, y1n and y2n, you must remember they are all sequences, they are not points, they are not numbers. x1n is a whole collection of numbers indexed by the sampling index n, and so too is x2n, so too is y1, so too is y2. So, it is not enough to look at a few points n and come to conclusions. You are talking about the whole integer set denoted by n obeying what we are saying here. It is superposition point by point on the index n. So, not only is it a superposition principle for all possible x1, x2, alpha and beta, that superposition holds pointwise. At every n this holds. So, now we understand that it is a serious demand that we are making on the system, right. This is the property of linearity. Now, let us break this property into two smaller properties. So, linearity has two properties embedded. One property is what is called additivity. And additivity is the restricted version of linearity, where we are only asking for linearity, but with alpha equal to beta equal to 1. So, essentially we are saying, if I take two inputs x1 and x2, if I were to add them, the outputs corresponding to x1 and x2 would also get added. That is what additivity means. And the other restricted form of linearity is what is called homogeneity or scaling. And that is essentially linearity, but only for well, this is tricky, only for x1, that is x2 equal to 0. So, it is a 0 sequence that we apply for the second. What it means is, I essentially give an x1, I study the output, x2 is anyway 0, I take alpha times x1 and give it to the system, the output should be alpha times y1. So, essentially homogeneity or scaling says, when I multiply an input by a constant, the output is multiplied by the same constant. Now, I break linearity into these two properties because there are examples of systems which can obey one but not the other. I am now going to illustrate examples of all the three: systems that are linear, systems that obey additivity but not homogeneity, and well, I will leave the third one to you as an exercise. Is that right? So, I will take the first two. Linear system example. We describe a system by the following equation. Well, how do you specify a system? A system is specified by the way it relates the input and the output samples. More generally, a system is specified by a mutual relationship between all the output and all the input samples, but it is more convenient to use what is called a calculable description. A calculable description means I can explicitly determine sample by sample the output from the input, and we will most of the time prefer to use what are called calculable descriptions. Otherwise, if you have an implicit relationship, so I can say y of n squared plus x of n squared is a constant, that is an implicit relationship, but it does not help me calculate yn from xn. So, we will most of the time try to use explicit relationships. Anyway, that is a technical point. So, let us take the example of a system where the current output sample is x of n is given by the current input sample plus the previous input sample. Since we are just beginning on our discussion of systems, I am trying to be very clear what we mean, but after a while we will not do this. In fact, let me go a step further. Let me take any linear combination. Let me take 3 times the current input sample and 4 times the past one, and let us show the system is linear. Well, the argument is very simple indeed. And I recommend that you pay careful attention to the steps of the argument, because this will be useful in other examples as well. We note, of course, that x1 n would result in the output y1 n is equal to 3 times x1 n plus 4 times x1 of n minus 1, and we use the same multiple notation because the same thing happens to x2. Now, let me give it alpha times x1 plus beta times x2. And let us write the output down on the next page. Now, you must be careful. Here it is all right, because you can, it is almost transparent. The output is going to be 3 times the input here plus 4 times the past sample of the input, and let us write that down clearly. The output is 3 times the current sample, alpha times x1 n plus beta times x2 n plus 4 times the past sample, but the past sample is also alpha 1 of x1 minus n minus 1 plus beta times x2 n minus 1, and of course, it is easy to see this can be written down as alpha y1 n plus beta y2 n by combining terms with alpha and beta. Simple enough. You just expand the brackets, you get terms combining alpha and beta there. You would have alpha 3 times x1 n plus and so on. So, I leave that to you to complete. So, it is very clear this system is linear because this happens for any x1, x2, any alpha, beta. Is that right? Now, let us take an example of a system which is not linear at all. Non-linear system. Well, very simple, take any non-linear operation. You could have x squared n plus x squared of n minus 1. So, I square the current input sample and add to it the square of the past sample. and I leave it to you as an exercise. Show that superposition is disobeyed. I leave it to you as an exercise to show that it is disobeyed. Well, what I mean by disobeyed is, now you must understand this point here. By disobeyed, I mean that I must produce one counter example. Okay? So, well, in fact, I leave it to you as an exercise to consider the following two inputs. Exercise hint. Consider the following two inputs. X1 of n is equal to 4 for all n, and x2 of n is equal to 5 for all n, and show that in this case it will be violated. Okay, so I am giving you, so you see, it is very important when you in general deal with proofs, that when you want to make a positive statement, so you are trying to prove a system is linear. Notice what we did, we were trying to prove a system was linear. The way we proceeded is independent of example. We said take a general input x1 or x2 and proceed and then come to some conclusions, and the conclusions did not depend on the particular alpha and beta that we chose. Then we sought to disprove or to prove against a particular statement. So, we wanted to prove the system is not linear. Now, there one counter example is enough. So, once I take this troublesome input and I prove that the system does not satisfy linearity or superposition for this, it is enough for me to conclude the system is non-linear. But the reverse is not true. If I take some examples and I notice superposition is obeyed in those examples, it is not adequate to conclude the system is linear, and in a minute you will understand why. Let us take the following system. Y of n is the real part of xn. Now remember, xn can in general be complex. We will show this system obeys additivity but not homogeneity. In fact, it is very clear that real part of x1n plus x2n is equal to real part of x1n plus real part of x2n. So, additivity is of course true. However, if xn is real, real part of jxn is not equal to j times real part of xn. In fact, if xn is real, the real part of jxn is 0, identically 0, and therefore, the system is not homogeneous. Now, here you could have run into trouble had you taken two real inputs x1 and x2 and tested homogeneity on them only with real constants. So, you could have in principle taken an infinite number of examples where you have real x1, x2 and real alpha and beta, and you observe superposition to hold, but the system is not homogeneous in spite of all those being true. It is not linear. Therefore, the system is not linear. It obeys additivity but not homogeneity. Now, I leave it to you as an exercise to construct a system which is homogeneous but not additive. And I give you a hint in the direction of this exercise. The hint is, typically when you take what is called an ordered choice of numbers, so if I have a list, or if I have a collection of a few samples of the past, And if I take, I order that collection according to its amplitude or magnitude, and then I choose one of those, maybe the greatest or the least or one of them in the middle, and I do this consistently as I proceed, then that process tends to be homogeneous. But I am giving it to you only as a hint. That is one possible case. But there are other ways to do it too. There are examples of systems that are homogeneous but not additive, and I leave it to you as an exercise to construct them. And there too one needs to be careful in the same way. One cannot simply come to conclusions based on specific examples. So, what I am trying to emphasize is, proof positive statement means prove independent of example. Proof negative statement means take one counter example. Now, when you want to negate a statement, when you want to disprove a statement, it is not always possible to come out with a whole class of situations in which that will be violated. It is not always convenient to do that. If you can do that, that is of course wonderful, but it might not always be possible. It might often be easier to construct a specific or a specific set of counter examples, right, which would disprove a statement. Anyway, that is so much so for principles of proof and disproof. And now we make one more observation. The observation, and this again I leave to you as an exercise, is prove. Now, here it is a positive statement. You need to prove it independent of example. Prove that additivity plus homogeneity or scaling together imply linearity. In fact, it is both ways. This way has already been shown. It is already shown because the very definition of additivity and homogeneity includes specific cases of linearity. So, if a system is linear, of course, you know that it obeys additivity and homogeneity because of the very definition. But the other way is what you need to prove, and I leave it to you as an exercise. So, if you are guaranteed a system is both additive and homogeneous, it is also linear, and I leave the proof to you. Yes. So much so then for the first of the properties that we wanted to discuss. The second property is equally interesting, and that is the property of shift invariance. To test the system for shift invariance, we need to perform only two experiments. We first apply to the system an input xn and study the output yn. And then we take the very same system S, apply to it the input x of n minus n0, where n0 is an integer and a constant. And the system is shift invariant if and only if the output is also y of n minus n0. Now, here again some things need to be qualified. Firstly, that this needs to hold for all xn and this needs to hold for all n0. This is very, very, very important. This is the statement formally, now we need to understand it. You see, the statement is that when I shift the input by an integer number of samples, please note we are only asking for n0 to be an integer. So, when I shift the input by an integer number of samples, the only consequence on the output is that the output is shifted and by the same number of samples. That is important. Not only that, this holds for every possible input and every such shift. So, when I wish to prove a system is shift invariant, I must prove it independent of what input I have given it and independent of what shift I have given the input. This is important. Of course, when I want to disprove, I only need to take a counter example. And now let us take an example of both. Let us take an example of a shift invariant system. In fact, we can go back to the very system that we had discussed as linear. So, take the system y of n is 3 times x n plus 4 times x of n minus 1 that we had taken a minute ago. Now, if I were, this is so, what it means is when I put x n into the system, I get y n according to this. Now, if I were to put x of n minus n 0 into the system, it is a very small subtle point, but what I would get, you see, how would I get the output? I would get the output by replacing n by n minus n 0 in both places. So, the output would be 3 times x of n minus n 0 as expected plus 4 times x of, now replace n by n minus n 0 minus 1, okay. That is easy. And of course, it is very easy to say that this is equal to y of n minus n 0. You see, because when you replace n by n minus n 0 here, you get exactly the same expression. This is y of n minus n 0. So, it is not too difficult to visualize what is happening here. At every point in the output, you are taking 3 times the present input sample and 4 times the past one. So, if I were to shift the whole input by n 0 samples, at every point I would be getting the same input but shifted by n 0 samples. So, whatever was happening n 0 samples before would now happen at this point, right. So, it's, even intuitively it is not too difficult to see the system is shift invariant. In fact, it looks like shift invariance is a trivial property. We expect this to happen rather too frequently, but we will see in a minute that we can easily construct a counter example of a system which does not obey this. So, let us now take a very simple example of a system which does not obey this. So, let us take the system y of n is n times x of n. Now, one remark here, typically shift variance, that means disobedience of shift invariance, tends to happen when you are looking at the clock in informal language. So, if a system looks only at the input and does what it wants to, the system tends to be shift invariant. But when the system also takes a peek at the clock underlying the input, then shift invariance is disobeyed. Now, in this system, the output at a given point in time, the output at the point n is the input at the point n, and the system is all the time sneakingly taking a look at the clock. So, it looks at the sample instant and multiplies by the sample instant. That is where the problem comes. So, now let us take 2 inputs. Let us take x n, now we bring in some notation. We bring in a very important sequence that we will often use. We call it the unit impulse sequence. We will use this sequence very frequently in future. We will denote it by delta n, and this sequence is 1 for n equal to 0 and 0 for n not equal to 0. So, it is 1 only at one place, it is 1 at n equal to 0 and it is 0 everywhere else. Now, I encourage you to work out what happens when this input is shifted by 3 samples forward. Find out the output. In fact, I ask you, what is the output in this case when I give an input which is 1 at n equal to 0 and 0 everywhere else? What output do I expect? 0 everywhere, because the place where it is 1, n is equal to 0, so it gets multiplied by 0. Everywhere else the input itself is 0, so it gets multiplied by 0 anyway, right. So, in this case, yn is equal to 0 for all n, when xn is equal to delta n. This, I repeat, this sequence, this unit impulse sequence is going to be very useful to us in future too. Now, let us find out what happens when we give the input delta n minus 3. So, I ask you, what happens when we give the input delta n minus 3? That means essentially, now what is delta n minus 3? Delta n minus 3 is going to be equal to 1 when n minus 3 is 0 or n equal to 3 and 0 else. So, it is 1 only at one point, that is n equal to 3. Now, what is the output going to be? The output is going to be at the point n equal to 3, it is going to be multiplied by 3, and therefore, we can write the output. In fact, we can write the output down explicitly, we can express the output in terms of delta. Yn in this case is 3 times delta n minus 3 when xn is equal to delta n minus 3. In fact, we can generalize this. In general, yn is equal to capital N times delta n minus capital N whenever xn is delta n minus capital N for any integer n. And obviously, this system is not shift invariant. If it were shift invariant, then I should have got the output 0 here too, but I do not. And you see why it is not shift invariant. The disobedience of shift invariance has come because the system is sneakingly taking a look at the clock when finding the output. When you bring in the clock in your output, there is a problem. Shift invariance is disobeyed. We need to take a break at this point to reflect on where we are. We have dealt with two very important properties, linearity and shift invariance. We now need to deal with others like stability, but we will take a break, as I said, and look more deeply at just these two properties, because together they give us a great deal. If a system is linear and shift invariant, then we will now prove a very important result, and the result is I need to perform just one experiment on that system to characterize the system completely. Only one experiment required. And in fact, that experiment will involve the very sequence that we mentioned a minute ago, namely the unit impulse sequence. I told you that unit impulse sequence is very important. It tells us a great deal, and it will tell us a great deal in context of linear shift invariant system. So, we will show that the following is true. A linear shift invariant system is completely characterized by its response to a unit impulse sequence. Delta n. We need to take a minute to reflect on what is meant by complete characterization. When would I say a system has been completely characterized? Let me ask you, when would you say a system has been completely characterized? Yes.
Whenever you give any kind of output, if you know what will be the expected output.
Okay.
All the frequency components are excited.
Frequency. So I'll repeat some of the responses I have. One response says that I know the output whenever I give it an input. That's one. The other response says that I'm trying to excite all frequency components. Any other responses? Yes. The relation between the input and the output can be determined. Okay. Yes. The same thing. All right. There's another transfer function can be obtained. Yes. Yes. You can predict the output for any input. Yes. Any input signal, can you repeat that? Any input signal can be constructed from, but how does that characterize the system? He says any input signal can be constructed by, that doesn't tell me that the system is characterized. What do you mean by, my question is, what do you mean by characterizing a system? You know, I'll tell you a story, and I think the story is relevant before we conclude the class, because very many of you must be studying this subject after possible exposure to some of the concepts in other contexts, right? There is a story of a master and a disciple, and the disciple was asked to bring a cup and a jug of water, right? So, you know, the disciple was asked to fill the cup partially first by the master, and then, you know, the disciple was again asked to continue pouring water into the cup even after it reached its brim. Naturally, the water began to overflow, right? After a while, the disciple wondered why this was being asked of him, right? Why am I continuing to pour water into a cup which is already full? The master said, that's exactly what I'm trying to point out. If I need to explain certain things to you, it's important that you have space in the place where you store what has been explained, right? If you come with that storage full, it's very important to put something into it. So, for example, the question here, I bring this up in this context because very often we already have our notions of what systems need to be like, what system definition. For example, some people, I'm not trying to dissuade response, but I'm just trying to tell you that it's important that you begin with the assumptions that have been made and the question that has been asked and the context that is being addressed, and not try to bring in extraneous things when trying to understand concepts. For example, some people mention transfer function, some people mention frequency. Now you see, at this moment we are just asking what characterizes a system. We have not said anything about we don't even know if the system has a transfer function, and if we don't even know if the system has been given a sinusoidal input, right? We just know the system has an input and an output, and our answer naturally should be related to that. So we don't bring in things, and you see, when we try and answer questions that are fundamental to the subject, it's very important only to proceed from assumptions that are made there, right? So here we have not made an assumption about any transfer function, or we don't even know if a transfer function exists. Similarly, we have not even made an assumption about any particular kind of input. So characterization, so in proofs or I mention this as a word of caution because it is very easy sometimes to be misled by our knowledge in other contexts, right? For example, some people think characterizing a system means being able to write an explicit relation between the input and output. No. Characterizing a system means just one thing. It means that no matter what input I give it, I know what the output is. And that's all that we can say, because we are just talking about a general system at this point in time. We have no knowledge of whether the system, you see, we are of course going to characterize a particular class of systems. But then the question that is before us is what is meant by characterization. Characterization means if I give it an input, I can determine the output. Whether I can determine the output by an explicit relation or an implicit relation or by observation is a different issue. In fact, now we will soon show that the output can be determined constructively. Constructively means I can actually write down a process by which I can construct it, but that's a bonus that you get, right? It's not a part of characterization. So let's make a statement about characterization. Characterization means being able to determine the output given any input. In fact, there is nothing more to a system, right? If I know the output for every input, the system is determined, it is characterized. Anyway, now we shall proceed to prove this in the next lecture. But what I will do is to give you what I call a trailer of the proof. And the trailer of the proof is as follows. You see, what we will show is that, as one of you said, any input can either ultimately be thought of as a combination of unit impulses appropriately shifted. Now, because a system which is linear and shift invariant has two properties. One is, since it is shift invariant, if I know what it does to a unit impulse, I know what it does when I shift the unit impulse. Because it is homogeneous, I know what it does when I scale the impulse. So, if I put a unit impulse and multiply it by a constant, I know what the output will be. Further, if I take two such impulses located at different points, and if I add them, I know what the output would be, if this were given. So, I use these three parts of the system description: the shift invariance, the additivity, and the homogeneity. By using these three properties together, we shall prove this theorem as the first step in the lecture to come. Right? With that, then we conclude this lecture. We will meet again for the next one.